second common type of nuclear decay is known as beta decay. So in beta decay, we essentially have an electron being released from the nucleus. So during the process of beta decay, a neutron inside the nucleus is converted into a proton and an electron. So as we've seen, the weak nuclear force is needed in order for this to take place. So our equation for a common beta decay can be written as AZP, where A is the mass number, Z is the atomic number, and P stands for the parent nucleus, decays into a daughter nuclei, which we can represent with the mass number A and the atomic number Z plus 1, plus an electron, which is our beta particle, which we can write as 0 minus 1 e. And then we actually also need an anti-neutrino, which we can write with the Greek letter little nu, and then the line over the top indicates that it's an anti-neutrino, and in this case it's an anti-electron neutrino. Okay, so during this process, we essentially have that neutron being converted into a proton plus an electron. So you can see that charge is conserved because the neutron has no charge, and the proton plus the electron, which it's being converted into, when we add those charges together, once again, we end up with no charge. Now the atomic number in this case actually increases because one of these neutrons is transmutating into a proton. So we now have one additional proton. The nucleon number, however, remains conserved. So initially we had a certain number of neutrons plus protons. Afterwards, we have an additional proton, but one less neutron. So the number of neutrons plus protons remains the same. Now, there's various reasons that we need the antineutrino created in this case. It's actually needed so that this reaction obeys the conservation laws. So we need it to maintain the amount of angular momentum, and also so that something called lepton number is conserved. So when we're learning about the standard model, we'll look a bit more into what this lepton number is. Now, as well as creating electrons through beta decay, this is known as beta minus decay because electrons are negative, we can create anti-electrons, which are known as positrons. So it's also possible for a proton to actually decay into a neutron and an anti-electron. So in that case, an anti-electron has a charge of +1, the opposite of the electron's charge, and the proton has the charge of +1 as well. So once again, charge is conserved. So in this beta plus decay, where we're getting the anti-electron formed, the positron, we can write the nuclear reaction as AZP, standing for the parent nucleus, goes into a Z minus 1 P plus 0 plus 1 E, so that's our positron, and in this case we get an electron neutrino produced as well, so that's nu subscript E to stand for that. So an example of beta decay occurring is with 234 thorium, which decays into 234 protactinium. So let's have a go now at calculating the amount of energy released in such a decay. Okay, so we're now going to be considering the beta decay where we have 234, 90 thorium, which is decaying into 234, 91 protactinium. So we need to start by writing down the reaction for what's going on. So in this case, we can see that the atomic number has increased. So we must be undergoing beta minus decay. So we're producing an electron in this decay as a neutron is converted into a proton, and then because we've got an electron produced, we also have an anti-electron neutrino produced. Okay, so we've been asked to calculate the amount of energy that's released in this decay. So the energy will be released as kinetic energy, which the electron and the antineutrino have. So they can distribute the energy between themselves however they want. But to calculate this amount of energy, what we'll need to do is work out once we know the mass of the thorium and the protactinium, we can work out the change in mass, and that change in mass is converted into energy. Okay, so the information that we need is that the mass of this thorium isotope here is equal to 234.043601 U. And for protactinium, the mass of this isotope is equal to 234.043308 atomic mass units. Okay, so the change in mass is equal to 234.043601 minus the 234.043308, and this is all in atomic mass units. So this is equal to 2.93 times 10 to the minus 4 atomic mass units, which, to get it into kilograms, we need to multiply by 1.66 times 10 to the minus 27. So doing that, we get 4.865 times 10 to the minus 31 kilograms. So now what we want is our energy. So E is equal to mc squared. We've calculated our m here, so that's 4.865 times 10 to the minus 31 times c squared, which is 3 times 10 to the 8 squared. Solving this, we get 4.379 times 10 to the minus 14 joules. Convert it to electron volts by dividing by 1.602 times 10 to the minus 19, and we get 2.7 times 10 to the 6 electron volts, which we can write as 270 kilo electron volts. Okay, so this is the energy which is released, and it'll be stored as kinetic energy in the electron and the antineutrino.